You don't have to. Okay. My next page. All right. A wave is a disturbance that moves through matter or empty space. The most important part is the next sentence. Waves do not carry matter. They carry energy. Actually, they transfer energy. So, back at the beginning of the school year, y'all took a little pretest for me. And I can't find the paper now. They talked about a beach ball. Do y'all remember this question? And if the beach ball makes it to shore, here it is, look. Two brothers playing soccer on the beach. One kicks the ball hard. Ball lands in the water 50 meters from the beach. They wonder, will it float back to the beach? Blah, blah, blah. Okay, like every sixth grader missed the question. Like 100%, seriously. So y'all all think that the waves will carry objects as they travel through the water. If we wait, the waves will move the ball back onto the beach. That's what everybody chose. No. The correct answer is Brian. Waves don't carry things as they travel through water. So let's talk about that. Did y'all do this red? Okay. So basically, what happens is, we could think of like this rope right here, and the ball is the little green thing. Grab that. Pick that up, girl. Right? Does the green thing make it to her? Does it make it to me? No. Up and down. You see what I'm saying? Waves will not carry an object. Okay, so think about a surfer. Because, you know, that's the argument that most people have for me is, well, how does the surfer make it to shore? If waves don't carry an object, how does the surfer make it to shore? Okay. Nope. Think about the surfer sitting waiting. He's waiting for the perfect wave. What does he look like? He's sitting on what? He's sitting on the board, and what's happening to him? Yeah. The weight, like, think about him. He just does like this. Like, the waves just move him up and down. Does he actually go far? No. But when he sees his wave, what does he do?
He swims back to shore.
But he paddles. Right? When he wants his wave, he paddles and he accelerates himself. If you think about yourself in a wave pool, if you're on a float in a wave pool, you don't make it back.
Does the wave have like an extra push?
No. Okay. The wave makes an incline. Do y'all see my little ramp over there? Okay. If you put a golf ball in this ramp, obviously what's going to happen to it? It's going to roll, huh? What made it do that?
Gravity.
Gravity.
Yeah.
So when they're at the top of the wave, what part are they on? The crest. And it's at an incline. So what's going to happen? Gravity's going to pull them down. That's how they ride the wave. The wave doesn't carry them. Gravity makes them move. Does that make sense? Now, what's going to happen on the wave is, what kind of energy am I going to have at the highest point? Potential. And then as soon as I start to go down, they transfer energy. Does that make sense? A wave transfers energy, but it does not carry things. So the wave doesn't actually move something across. Now, like if you're in a wave pool and you let the wave carry you back to the shore, it's because you like accelerated yourself first. And then you know what I'm saying? You have to accelerate yourself first. Other than that, you're just going to stay in the same little... Now, current is not waves. Current is not waves. A current happens because it's like rivers and streams and all that. They start at a higher location and they go down to a lower location. That's how you get current. But that's not a... I mean, you could have waves in your current, but that's not like crest, trough. Does that make sense? Yes, so current is different. It is accelerating you because it's moving you from high to low. Okay? Okay, so I put all the T's in red. Transverse waves have vibrations of particles of matter that move back and forth at right angles. Perpendicular. That's what that T is. Remember perpendicular to the surface? Perpendicular to the direction that the wave is traveling. So the direction that the wave is actually traveling... Oh yeah, I forgot to put that on everybody else's. Let me see how she did that. That's the wave direction. And then we have the right angles. At the top part. Here, let me see. It doesn't matter. I just told you what I did. Okay, the amplitude. Total distance a wave moves or oscillates, say it, oscillates, from its resting position. So oscillates means moving or vibrating. Okay, that's another word you need to know. This person had a really cool thing that I've never used before. Look at what they put in the middle of the amplitude. An A. It makes an A. So no one should forget that. Okay? The crest is the highest point. The trough is the lowest point. And then let's look at wavelength. So this makes it sound a little bit different, but I like it. The distance from one point on a wave to a corresponding point on the next wave. So I want you to have a drawing. If you did crest to crest or trough to trough, that's great. That's fine. But I want you to add in either a wavelength here, or it would be from this dot to a dot right there. Does that make sense? Because it's one corresponding point on the wave to the next. It's like in the same place on the next wave. Who doesn't understand or has a question? You got it? Y'all ready for the back? What do you want? You want pictures?
Yeah.
Yep.
I didn't get the pen.
Okay, I'll give you pictures. Yes, sir, for sure. Okay. Frequency. I did all this in red. The number of oscillations. So what did I tell you that meant? Vibrate or movement. Produced in a certain amount of time. Basically, the number of waves in a given amount of time. The number of waves in a given amount of time. Do you remember from your notes what 1 hertz is equal to?
1 second.
Nope.
It's a 4th second.
Nope. 1 hertz equals, it's on the paper, 1 hertz is 1 wave per second. Okay? 1 hertz is 1 wave per second. So, they want you to draw a wave with a frequency of 4 hertz. Wait, y'all tell me what that would be.
Oh,
4 waves per second. Okay, so it would look like that. Does that make sense?
what color should it
1, 2, 3, 4. It doesn't matter. You could do it in blue. It's okay. Just mark your... I want to see a wave where you have marked 1, 2, 3, 4. What if I said the frequency was 25 hertz? What does that mean? 25 waves per second. Keep it simple, okay? It's not as hard as you think. Okay? Good old speed. Y'all remember that? unfortunately. The distance a wave travels in a given amount of time, and look, here is meters per second. We remember that? How do we write that? Nope. Yep, remember that? Okay, so, no, that is acceleration. If a wave travels 6 meters in 3 seconds, what's the speed? How do I do this? Speed equals, look at your units. What's going to go on the top? What's meters measured in? Like what? No, like what measurement goes with meters? Meters is a measurement of what? Distance. And seconds is a measurement of distance divided by time. 6 meters divided by 3 seconds, 6 over 3, 2 meters per second. If a wave travels 10 meters in 2 seconds, what's the speed of the wave? It doesn't tell us. I mean, there's a calculation to get it, but I'm not going to make you go all backwards and all that kind of stuff. But we would have to know more information than that. Okay? All right. The bottom. Blue. So it says, answer each question and label each underlined word in the diagram below. So everything that's underlined, we have to label it in the picture. I'm still trying to color code it for y'all so we can keep all that straight. What is the amplitude of the waves? Okay, where do we find amplitude?
From base to top, from base to crest, from base to top.
Okay. There's no base. It's the rest position. It's in the, what did we just learn it looks like? The A. Yep. So, what is the amplitude of the waves below? Answer that question. What is the amplitude of the waves below? Janie says 0.5 meters. Who agrees? Who doesn't understand? Or you're not sure? The amplitude is how much distance it is from the rest. It's this. How much is? It's this. How much it is right there. So you see this line at the top right there? What's that say? So it's 0.5 meters. Okay, how do I draw a wavelength? Okay, you want it from here? Well, you want Well, my question is also asking what is the wavelength, so they want me to actually tell them.
Yeah.
Okay, but how are you going to measure that? No.
Oh, I know what you do. I do it from where the wave starts.
You could.
0 meters.
Okay. You could do it from here to here.
And that would give you the wavelength. Because it's a meters.
Yep. Or you could do from here to there. You see that? So I could have gone from 0 to 2, or I can go from 2 to 4. How much is the length of a wavelength?
2 meters.
2 meters. How many full waves are shown? Stormy, you know how many full waves are shown? 2. How many waves are generated in 2 seconds? 1. Total time.
Oh,
Does that make sense? So how many waves do we have? 2 in 2 seconds.
is something you want this to be said?
You could have questions like this. Yeah, you're analyzing a model of a wave.
I was going to say,
It's not. It's not. It's not a full. It's only like a little bitty tiny part. What is the speed? Distance divided by time. So what was our distance?
25 meters.
Nope.
I know it. It's 1 meter a second. It's 4 meters.
No. 4 meters
4 over 2. Oh.
divided by 2 seconds.
2 meters per second.
It's 2 meters per second. Where is a crest?
Right at the top.
The highest point. Where is a trough? The lowest point. Okay? I color coded it so we don't have to write everything. Now tell me, what's the frequency?
2 waves a second. Right here. Yeah, 1 wave a second.
What's the definition of frequency? So the number of waves in a given amount of time. How many waves? How much time? So what's the frequency?
2 waves. 1 wave per second.
1 hertz. Who doesn't understand? Who doesn't understand? Ask me a question. Okay. Because it's 1 wave every second. I mean, 1 hertz is 1 wave per second, and we had 2 waves in 2 seconds, so that is 1 hertz. Make sense? Okay. Awesome.
Are we done?
No. Of course not.
Oh, yeah, lucky.
How many minutes I got? 10 minutes. Okay, I can do this in 10. Here we go. I drew these better. Waves are not easy to draw. Blech.
As long as we know what kind of waves they are.
Yeah, but really and truly, all of the, like it does matter. They're supposed to look the same. Like whatever I'm drawing on here should look the same, and whatever I'm drawing on here should look the same. Okay? Okay, so we have frequency and we have wavelength. Let's draw our wavelength in. We're going to go ahead and just draw from here to there, and from there to there. Huh, do those look the same? No. Let's compare them. What do we think about this wavelength? He's longer, so we're going to say this is a big wavelength. And we're going to say that this one is we're going to call it just a small wavelength. Now, what's frequency? How many waves we have in a certain amount of time. So, which one do we have more waves on? This one, right? So when we have a small wavelength, what kind of frequency do we have? A bigger frequency. When we have a big wavelength, no, we have a small frequency. We don't have as many waves occurring. Does that make sense? You can clearly see that in the picture, obviously. So this is called an inverse relationship. And that means when one goes up, the other goes down. It's that simple. Yeah, you were supposed to see that that's way bigger than that. Okay? Which one of these two do you think would be more energy? Energy. You think this would have more energy? Because why? Why do you think so? It's got more waves happening. If you have more waves let me put you in the wave pool with barely any waves, and then put you in there with it like, I mean, it's going to be like this. That's way more energy. So this is big energy, big frequency. This is small energy, small frequency. Do you know what their relationship is called? Direct proportion. I've taught y'all all of this before. What does direct proportion mean? Direct proportion. Equal amounts. Right? If one doubles, what happens to the other one? The other doubles. What if it goes up by 500? Yeah, it's a direct proportion. Like your portion on your plate. Okay, last thing. 2 minutes. Whoa, what do we think about that? Which one has the most energy?
The right one.
For sure.
Because it's generating bigger waves and they're longer.
No, they're taller. Their amplitude. Yep, their amplitude is higher. So, small amplitude, small energy. Big amplitude, big energy. Energy is proportional to the square of the amplitude. I taught you about this with kinetic energy. What happens if I double the amplitude? No. The square. You have to square that. The energy is quadrupled. What if I'm not done. What if the amplitude is 3 times more?
You swear it?
What's the energy going to be? 9 times. Good job, Layton. You did awesome today.